afternoon, everyone. I'm Catherine Brookman, Associate Director, Knowledge Transfer and Exchange, and on behalf of Dr. Jack Callahan, Director of the Center of Research Expertise for the Prevention of Musculoskeletal Disorders, or CRE-MSD as we are more commonly known, we'd like to thank you for joining us today for this free webinar. We are grateful to the Ontario Ministry of Labour Training, Skills and Development for our funding, which supports the delivery of these webinars, and to our presenters who provide their expertise. We ask that you keep yourself muted for the duration of the webinar as a courtesy to the presenters and all participants. During the question and answer period, we ask that you type your questions into the chat box. The chat box can be pulled up on the screen by selecting the chat icon in the control panel that appears near the bottom of your screen. I will relay these questions to the presenter or a similar question should we have duplicate themes. Should you have a pressing question or issue such as a technology glitch that cannot wait until the end of the presentation, please type this into the chat box right away and we will do our best to address it. The format of today's webinar is as follows. The presentation will be given, after which time we will have 10 to 15 minutes for a question and answer period with our presenter. This webinar will be recorded, with the recording being made available to you on our website along with the presenter slides shortly after today's webinar. After the webinar, you will be sent a link to an evaluation. Please fill out this evaluation as it will assist us in the future delivery of our webinars. Thank you so much for joining us today, and remember to watch the CRE-MSD website and the MSD prevention website for new resources and events. Now it is my pleasure to introduce to you to our presenter, Dr. Nick Delfa. Nick is an assistant professor in kinesiology and director of the Occupational Neuromechanics and Ergonomics Laboratory at Ontario Tech University. He received his PhD in Occupational Biomechanics and Ergonomics from McMaster University, followed by a postdoc fellowship in shoulder biomechanics at the University of Waterloo. Nick's research program aims to reduce the prevalence of work-related MSDs through enhancement of our knowledge of human capability, function, and performance. Nick endeavors to translate his research into advanced methods that proactively assess injury risk, with a particular emphasis placed on the integration within digital human modeling and proactive work simulation technologies. By doing so, work tasks can be assessed virtually early in the design phase, well before they ever exist in reality, saving both workers and employers from the financial, physical, and emotional burdens of work-related MSDs. Thank you, Nick, so much for agreeing to present to us today. And now over to you.
Okay, Catherine, thank you for the introduction. And thank you to CRE-MSD for the invitation to present today on this topic. And I do want to acknowledge my former graduate student, Daniel Muller. He's off in medical school now in Dalhousie in Nova Scotia, but this was a lot of the work that I'm going to present today is his master's thesis work. So we were grateful to be funded by CRE-MSD through a seed grant to undertake a lot of this work. It was vital for me as I got started as an independent researcher to kind of get the ball rolling. So I just wanted to make that comment and thank CRE-MSD for the support in making this happen. So just to get started here, I'll just give a brief timeline, just maybe a little more detail than what Catherine mentioned. So I did start at McMaster. I spent 10 years there doing my undergrad, master's, and PhD. My master's and PhD were under the supervision of Dr. Jim Potvin. And actually, one of the very first studies that I conducted in his lab was a muscle fatigue-based study. So we were looking at EMG processing methods just to try to kind of figure out what was going on with the fatigue process in the quadriceps. So a lot of you, though, you might remember my webinar about 2 years ago where I've gotten more during my PhD into the development of the arm force field method. So I did dedicate a lot of my time kind of after that initial fatigue research. I thought I was going to go in that direction, but I ended up going into the world of the arm force field and kind of determining acceptable loads. So, but that's just to say that fatigue was definitely a major interest of mine, and it was something that both, Jim was studying in the lab, people like Mike Son, who was also a PhD at the same time as me. So it was definitely keenly interested in the topic. And that did prepare me too, where when I did go to the University of Waterloo, I did a postdoctoral fellowship with Dr. Clark Dickerson. And I really got into the world of shoulders, obviously shoulder modeling. And one of the main projects that I got a chance to work on was using Clark's shoulder model here and trying to incorporate a fatigue assessment module within it, just so we could evaluate some work simulation tasks proactively. So that was a really exciting project. I don't know if Clark's in the call now, but I am working on the paper finally. So hopefully everyone will get a chance to kind of see more of the details of that this summer. After my postdoc, I did go to Ontario Tech University, which is in Oshawa, Ontario, and I've been there since 2017. So the overall objectives and themes of my research, the overall goal is to reduce musculoskeletal injuries, primarily through the enhancement of ergonomic strength and fatigue assessment tools. And kind of with the forward vision of incorporating some of the more basic research on, human strength and the factors that influence it, as well as neuromuscular and mental fatigue, try to take those concepts and apply them into these digital human modeling and work simulation frameworks. Another thing that I'm very interested in is, more applied ergonomics research and kind of just taking some of the things we know and looking at specific tasks, like things like dental hygiene, for example, or in long-term care workers, things like using pill crushing devices. So this is kind of the main things I focus on in my research program. More specifically, I was lucky enough to be funded by NSERC to undertake this vision. And this is essentially how the things come together more specifically. The main goal, again, is to accurately estimate acceptable manual forces and torques. So the first part of that in my research program, again, is looking at human strength, right? That's both just understanding it as well as modeling it using things like the arm force field. And then, on the more basic side, understanding how things like sex and age can affect it, limb dominance, static versus dynamic exertions. Then on the other point of this is understanding more transient modifiers of strength. So things like muscle fatigue and mental fatigue is something that I'm starting to be a little more interested in too. And then looking at objective 1 and 2 together to work on this overall goal of accurately estimating acceptable forces and torques. And then, of course, the main application of a lot of this work is to try to incorporate it into some of the digital human modeling platforms that are out there right now. So basically, these all kind of feed into one another, and that's how I kind of plan my research moving forward. But the main topic of today's presentation is going back to the world of fatigue, specifically muscle fatigue. And it is one of those concepts in science and in the world that really has a whole bunch of different types of meanings. Fatigue can be more of a mental state, an emotional state. In material sciences, it can mean something, very different. So, this word cloud kind of does a nice job of it. So it ends up being pretty important to define what we're talking about in terms of muscle fatigue. And generally in the world of ergonomics, at least specifically physical ergonomics, looking at the muscle is the idea of muscle fatigue. And that's classically defined as some sort of exercise-induced reduction in the ability of the muscle to produce force or power. So kind of the main thing I wanted to distinguish here is that fatigue really is a process. It generally starts right after the onset of that sustained activity starts. It isn't necessarily a point in time that you can identify as saying, oh, yep, fatigue is there now, right? So it's a process, and that's important when we're trying to study it. Another thing I brought up, the CRE-MSD position paper from a couple of years ago, Marcus Young and Richard Wells, they define fatigue as a process that results in the impairment of well-being, capacity, and/or performance as a result of work. So that has more of a ergo-related context there. So let me just show this example. I'm sure everyone here is familiar with the idea and the feeling of muscle fatigue. So if you were to go and do a wall sit right now, at the beginning, that would feel relatively comfortable, but gradually over time, you'll start to feel that fatigue progressing, in your legs, specifically your quadriceps. And basically, if we were to take a look at how fatigue was progressing within that muscle, essentially the second you start that wall sit, your muscles start losing that ability to generate their force. Right? So this is showing as you go up the y-axis, it's a decrease in strength, right, as a percentage of your maximum strength. Okay, so you're decreasing in strength, which is your definition of fatigue. And then eventually when you stop doing that exertion, you're going to go into a period of recovery. Okay, so an important part about the progression of fatigue is that it really is a function of the effort that you're working at or the intensity you're working at. So if I were to put a medicine ball now in this guy's hands, right, we're going to be working at a slightly higher percentage of maximum effort. So let's say 30% effort. And if we were to do that, to get to that same level of relative fatigue of around 10%, it's going to take about 50 fewer seconds to get there. Okay, but you can see, again, if we stop that exertion, the recovery is roughly similar. Okay, again, if I put an even heavier medicine ball in his hands, again, you can see that it's going to take less and less time for that fatigue to accumulate. So you still hit the same level of fatigue, but the way in which you got there was slightly different. And that's an important factor to consider. Now, more occupationally, fatigue it's a little more different than our classic textbook examples like a wall sit. We have often very varied work. Some might be more repetitive in nature, very cyclical. Some might be more prolonged and static work, like working at a computer all day. I'm sure all of us now are familiar after the last 15, 16 months of sitting in maybe less than ideal ergonomics postures and setups, and maybe having some shoulder and trap fatigue or neck soreness, right? And then other types of work where you're kind of lifting boxes and other types of manual material handling work. So all have some level of MSD risk associated with them. And often there's a whole host of interacting work factors that we need to consider. So force, repetition, duration, those all need to be factored in. So, obviously, specifically, in this presentation, we're talking about the idea of localized muscle fatigue or persistent localized muscle fatigue. As I mentioned in the last slide, fatigue is a process, so it starts the second you really perform an exertion. But where it becomes an issue in the workplace is when you're not having enough chance to recover from that fatigue exposure. So you're coming back to work on multiple days not having recovered or brought that fatigue level back down to 0%. There's a mic on there. So if we do get into this status here where there's persistent localized muscle fatigue, that just means we're not getting enough rest. Those muscles are starting to be pushed and not having enough time to recover from the micro damage that occurs. That's when we start to see increased risk for work-related musculoskeletal disorders. Another thing we tend to see with that and associated with localized muscle fatigue might be diminished performance as well. So this might be metrics such as productivity, or even it can put you into a situation where maybe your safety is at jeopardy as well. So these are some of the reasons why we study this and we're so interested in fatigue and in ergonomics. Mainly, I just kind of want to address two issues here at the beginning of my presentation. First is how can we quantify muscle fatigue? And the second is how can we control muscle fatigue in the workplace? Okay, so likely most people would argue the gold standard for quantifying localized muscle fatigue is looking at a decline in strength. MVC, you'll see that throughout the presentation. That stands for maximum voluntary contraction. Right, so strength is basically what is that maximum voluntary output that you can do. That might be at the level of the joint, it might be at the level of the hand, a specific muscle if you can isolate it. But given the definition of fatigue is a reduction in your strength capability, it makes sense that this would be a very good metric to try to quantify. Another common approach we use is looking at EMG measures. So for those who aren't as familiar, EMG or electromyography are basically a way that we could put electrodes over top of the muscle, typically on our skin surface, and they record the underlying muscle activity or the electrical activity that's being sent from your brain down to your muscles. And we've gotten pretty good with our techniques in order to quantify what these what the EMG is doing and how much electrical activity are in our muscles. In terms of trying to quantify fatigue, typically what we observe is that, especially when you're doing a force exertion at some sub-maximal level. So here, say you're holding a force at 50% of your maximum, what you typically see is a rise in your EMG signal. Okay, there's a couple neurophysiological things that happen there, but basically you're just kind of needing, as your muscles fatigue, you kind of need to increase the signal and recruit more and more of your muscles in order to keep maintaining that force at that submaximal level. Another way that we can look at fatigue using EMG is looking at the EMG frequency spectrum. So that's kind of shown in this figure here. And again, if you're not familiar with this, basically what we could do is take that EMG signal, and within that signal, it's basically composed of a whole bunch of different frequencies or components, much like, say, a music signal. I'm sure many of you have seen kind of a frequency spectrum of music, and these can rise and ebb and flow based on the music. If music has a little more heavy bass content, you might see the lower region being a little bit more amplified compared to maybe if you have a more trebly song, this region might be higher. It's a similar philosophy here with the EMG spectrum. And what we've seen over decades and decades of research is that when your EMG becomes more fatigued, then we tend to see a shift to the left of the frequency spectrum, or more of the lower frequencies start to be amplified compared to the higher frequencies. So that's a useful tool for us. Another is using psychophysical ratings of perceived fatigue or discomfort. These are nice. They're not very invasive. We just ask people to be their, basically, what do they feel in their body, and kind of become their own sensors, right? So they can tell us maybe in a specific region of their body how much discomfort they're feeling. Or even more recently, we're asking them straight out, what is your level of rating of perceived fatigue right now? And I've kind of used this approach over the years, but I've always questioned, do the raters truly understand what they're rating? So I kind of addressed this question later on. So I'll get into that in a little bit. So really, these are 3 examples, maybe 4 examples, but back to that workshop a couple of years ago, I was actually, I think, a first-year PhD student at the time. So I kind of got, I was able to sit around the table for this when a bunch of fatigue experts from mostly around North America kind of got together to answer this question, kind of, how do we measure neuromuscular fatigue in the workplace? And, the workshop basically came up with all these types of variables that we can look at and link them to different factors. So things like performance and quality, injury and disorders, illness and wellness, discomfort. But basically you can see all of these things here and how they can interact. So there's a lot of different ways we can approach this. Okay, so it's a little bit messy, but I would say for the most part, at least in my research, and I would say a lot of researchers similar in the space, we kind of focus on these main metrics. So let me just give you a couple examples of using EMG in research. So one might be, here's that dental hygiene example here where we basically instrumented with kinematic sensors and also EMG. And then we were able to track how, let's say, the neck extensors, for example. Dental hygienists are often in that flexed neck posture for a major portion of the work period. And here, if we've compared it to some EMG limits that have been established in the literature, you can see a really high neck extensor exposure here, particularly at the static or at that prolonged level. So EMG gives us a really nice window into what's actually happening with those muscles. Right? And here's another example from this pill crushing study. Right? We can look at, or we can use EMG to compare between different muscles, and also we can study different types of conditions. So what heights, if we put this pill crushing device at different heights, what is the resulting effect on the underlying musculature? Right? So it's a great way for us to study what's happening. So as I mentioned, great for comparisons between conditions and factors, quantifying how much fatigue is developing, and comparing to standards. It's basically a window of how much muscle force are we actually generating. Right? And using this, it can result in recommendations and best practices. But as you all know, we can't just do an EMG study on every possible work task, especially ergonomists in the field. That becomes a big challenge. So how can we proactively prevent or control fatigue? do different work thresholds exist? And ideally, do those thresholds exist using more accessible inputs? So things like force, repetition, duration, things that we know about a task almost all the time. So, again, there's kind of a history in the development of this. We can go back to the work of Walter Romer, and he tried to balance effort and recovery time in a method. So kind of using this concept again, where based on how hard you're working as a percentage of your maximum, that's going to require a certain amount of recovery time to get back down, or a rest allowance. So this approach basically tries to determine how much rest will be required given you're working at a certain percentage of maximum strength. Okay. One potential issue with this approach, which is kind of being addressed more recently, is that it assumes if you're working at 15% of maximum or below, that no fatigue develops. And we know that that isn't quite the case. Another very common approach used in pretty much a lot of the ergo tools we have available to us are reducing load based on frequency and repetition. Okay, so I've kind of lifted these figures from Jim Potvin. But we have, when we're working at lower frequency levels, we can generally use higher loads, right? And this is more where acute injury tends to happen, when we're dealing with higher loads at lower frequencies. If we're going to be working at higher frequency now, that means that obviously we're going to be developing further muscle fatigue. So we need to lower the load that we're going to be working at in order to maintain an acceptable capacity over demand, or demand over capacity. And so this general shape of this relationship exists in a lot of the tools. So if you look at the Liberty Mutual psychophysical tables, and you kind of plot out how the maximum acceptable weight of lifts or pushes, how they change as a function of frequency, a lot of them follow this general pattern. Same with the NIOSH revised lifting equation. They also have the ability, based on certain frequencies or lifts per minute, it'll adjust what that acceptable load would be, or what the recommended weight limit would be. We see this in the AC-GIH TLV for hand activity level. This one doesn't show that nonlinear relationship here, but it does use something called hand activity level. So it's not directly frequency, but it is quite related to it. So that's reducing based on frequency, but frequency and repetition sometimes doesn't tell us the whole story, because we could have a situation where this represents 10 repetitions per minute, right? So you're going on, then off, then on, then off, right? So let's say that this is 10 repetitions per minute. This would be a 50% duty cycle, okay? And just duty cycle basically tells you how much time are you spending producing an effort relative to the overall time that you're performing that work task, okay? But if I were to show you this scenario here, this is also 10 repetitions per minute. Right, you're still kind of doing those 10 exertions, but because they're not going on for quite as much time, they're basically half the length of each of these exertions. This is only a 25% duty cycle. Okay, so that information could get lost if we're only looking at repetition. So this is the advantage of looking at duty cycle, which basically accounts for the overall time you're producing effort. Okay, and this is what Jim focused in on when he developed the maximum acceptable effort equation. I think this has been a prior CRE-MSD talk as well. But basically, he looked through a lot of the psychophysical literature, specifically for the upper extremity, and found studies that would be appropriate for this analysis. And without going through the whole thing, one of the big factors here for inclusion is that he needed to be able to figure out what the effort durations were for each of those repetitions. Okay, thus being able to calculate duty cycle. Okay, so we ended up on this selection of studies and their various conditions. Okay, and when you look and plot what the maximum acceptable effort was, so basically those are psychophysically derived. They got people to work for long periods of time, and they use their bodies to say, this is what the acceptable load would be that I'm comfortable working at. Right, so if you plot maximum acceptable effort versus frequency, using all of that data I showed, it's not necessarily the greatest relationship that emerges here. And a lot of this can be explained by that prior example I showed you. But when you adjust the frequency to duty cycle, you can see that nonlinear relationship starts to emerge here very nicely. Okay, so Jim fit an equation through this, and this is what became the maximum acceptable effort equation. Okay, and the nice thing is it actually fits lifting and lowering data very well. So there's something about the shape of this curve, something to the power of 0.24, which really does a nice job estimating what an acceptable effort would be based on duty cycle. So I'll just give you another example. Just checking my time here. So how can the MAE be used in practice? So this is an example from if someone were to use the arm force field in Santos, right? So you can run analysis. Let's say we're evaluating 45 newtons of force, right? We can run the arm force field. It would predict a 1 rep maximum of 89.1, right? That would be the strength that's predicted for that condition. Okay, so this, we can compare the 45 to the 89 and determine that a large proportion of the population can do this. So this would be what we would consider to be acceptable in a basic analysis. Okay, but what if this task is repetitive? What if it has a frequency of 12 efforts per minute, and we know each of those efforts have a duration of 0.7 seconds? Well, we can basically, again, figure out what our strength is, and then that strength becomes the 100% here. And we can multiply that strength then by the MAE correction. Okay, so whatever duty cycle we're working at, that'll tell us what our maximum acceptable effort is. Okay, so then that's how we can account for this. Okay, so again, I'll kind of spare the math here, but if we were to plug these values into the equation, you would get a predicted MAE of around 38%. Coming back to our example here, if we take our 45 newtons, you input those parameters, it calculates a 38% MAE. Now that would adjust that final recommended force limit. So that 45 newtons now becomes unacceptable. So this is using a digital human model, but the same thing can be done just using normative strength data to figure out what our 100% is. Okay. All right, so this leads me in to the ACGIH TLV. So this is, again, a governing body based out of the United States, and they document various threshold limit values. It can be for things like chemical exposures, radiation, but they also look at musculoskeletal exposures as well. And they developed a TLV for the upper limb localized fatigue. And they actually used the same approach. They used the MAE equation as their basis, and they added in some more recent data that had been published from Mike Son and Jim. And they fit their own curve through the data, which basically gave a very similar shape. Just a few differences. They didn't really allow their equation to go up to 100%. And they, especially with duty cycle as well, they stopped it at 90% and didn't allow it to continue forward. So just slight differences, but overall the same philosophy was applied. Okay, so when you compare the two, you can see they're very similar in shape. Slight differences mainly, again, due to kind of the anchoring points of these two equations. Okay, and you can see, especially once you get into higher duty cycle ranges, that's where some of the largest differences are observed. So the red here shows the difference between those two curves. And you can see that that difference becomes more exaggerated as duty cycle increases. Okay, so we have these approaches to control fatigue for isolated tasks. They're based on psychophysical data, which are generally very robust, especially it's been validated on lifting and lowering and other scenarios as well. It provides actual threshold levels that we can use to adjust force levels based on duty cycle primarily. Right? So it's nice to have something that can give you a line in the sand. But some questions with this: how does our body actually respond when we're working at, above, or below these threshold limit values? Right? And then how does fatigue manifest itself if you're working at different portions along this curve? Right? So these are more of like a validation idea, just moving forward, just trying to test what are some of the physiological responses based on the thresholds that are determined by these methods. So that's kind of what this project is mainly centered around. We wanted to determine, is the amount of fatigue development the same at different points along this curve? We chose the TLV as its official guideline in the United States. We went with the TLV for this comparison. And it basically kind of tells us, is the amount of fatigue development going to be resulting in more of this scenario where we have enough of a rest allowance, we're not accumulating fatigue over time, or is it going to be a scenario where we are developing too much fatigue? So that's kind of the goal of this particular CRE-MSD funded project. We did, though, so that was the main goal, but we did want to do a quick study first, and this centered around the idea of RPF. Can we improve accuracy of our ratings of perceived fatigue? Right? And this is just having used this approach before, it just seemed that a lot of my participants were giving wildly different estimates of rating of perceived fatigue. So it really just kind of let me believe they just didn't really know what they were rating. They didn't know what they were supposed to be evaluating. So we wanted to do a quick study that allowed them to get a chance to get some very specific feedback on rating of perceived fatigue to see if we can improve that and make it a more valuable metric moving forward. Right, so before I get into study 2, which really looks at the current thresholds, I'll just quickly share what we found with this RPF study. Okay, so we know it's strongly correlated to force declines in EMG measures, but there's inconsistent provisions of scale familiarization. You know, some people will try to give different anchor points just to frame it for participants, but it often still seems to be misunderstood. Okay, so this is a paper we had published relatively recently, and it asks the question, does a period of familiarization improve the accuracy of rating and perceived fatigue relative to those classical measures of localized muscle fatigue? So those things that I shared with you earlier, like force output, EMG amplitude, mean power frequency. I basically want to see, can we get RPF to behave just as good as some of these other more gold standard metrics? So we had people come, we isolated the biceps brachii here. We had them doing elbow flexion exertions at 50% of MVC. And we had 2 groups here. And these groups came in on 3 separate days. On day 1, they did a fatigue protocol. So they just kind of continued this protocol in cycles just until they couldn't do it any longer or 1 hour had elapsed. Then on day 2, our 2 groups did something slightly different. So the control group just repeated the exact same protocol. But then we had another group that received more specific feedback on what their RPF was relative to their strength decline. I'll show you that in a second. Then on day 3, they came back again and we did a retention test. So again, we eliminated or removed any feedback, and both groups, again, we saw how they were able to rate their RPF. So just quickly, you know, this would be an example of a task cycle. So they're working, it was a high workload, 50% at a 50% duty cycle is very demanding. It would be well above the TLV. So after they completed a cycle, we would get them to use a visual analog scale to rate their perceived fatigue. And then after that, they did an MVC. And then right after that MVC, we calculated what was their decline in strength. And for the feedback group on day 2, they got that feedback. So they were able to essentially calibrate themselves as they moved through this fatigue protocol. So now we're at a later cycle. And we can see that they've rated their fatigue here. Again, they do their MVC and get feedback. And they can see now what is their RPF relative to the strength decrease. Okay, so it's just a way to kind of give that feedback and just give them a sense for, you know, how can I rate RPF consistently? Okay, so we looked at EMG amplitude, mean power frequency, again, RPF, as well as a decline in MVC. And we normalized everything. We time normalized as well as fatigue normalized. So everything was kind of on the same scale. And then we calculated average error and root mean square error between RPF and MVC, RPF and EMG amplitude, and RPF and mean power frequency. Okay, what we saw on day 1, again, this is the error between our MVC, or our force decline, and rating and perceived fatigue. So we could see a relatively big error on day 1. They had no feedback at this point, just general basic instructions. On day 2, this is where we gave the feedback group that training, or that feedback on what their RPF was relative to their strength. And we can see that their error decreased quite a bit, significantly decreased. Okay, and then when they came back on day 3, they essentially retained that knowledge. So they were able to rate RPF, again, with a lot lower error relative to the decline in strength. Okay, here, this just kind of shows a similar thing, but it's showing average error. Okay, so this has some directionality to it as well. And again, we can see on day 2, feedback errors decrease. On day 3, the average error is actually almost minimal for that feedback group, meaning that their RPF was mapping on to their strength decline relatively closely. Okay, we also saw similar improvements in RPF relative to mean power frequency. Okay, so you can see similar shapes here. So again, the overall conclusion is that RPF scale familiarization really improved the accuracy of RPF relative to measures of force output and measures from the EMG signal. So this could be a really valuable tool for us, both for researchers and practitioners. You know, we use this all the time. All this study really showed that if we take a little bit of extra time at the beginning and really give them some specific feedback on what their RPF is relative to actual fatigue, then this can become a very valuable metric. Just one of the things that makes this important is that, and one of the tricky things in general about fatigue research is that measurement of our gold standard metric, or MVC, adds to the fatigue that's being developed. So the instrument that we use to detect fatigue is actually causing more fatigue. So that could be a problem in some of our experiments. Okay, so if we can really get RPF working well, this can help circumvent this issue. Okay, so thanks for obliging me on that. We got a little bit extra out of that CRE-MSD seed grant, so we were happy to be able to do that. So the next part of this, the main topic of the presentation, is the evaluation of current thresholds of exposure for upper extremity work. Okay, and the idea here, the main research question was, again, to evaluate localized muscle fatigue responses at 3 workloads along the upper limb TLV. So we selected the 20%, 40%, and 60% duty cycle, right? And we determined what would the TLV recommend that percent MVC to be, or the maximum acceptable effort to be. Okay, and then we set up our experiments basically mimicking this exact scenario. So the 20% condition, this is what it would look like from a force exertion profile. It would be around 30% of contraction at that 20% of a duty cycle. Then after a cycle, we would get RPF, RPE. We took some psychological measurements as well, just to make sure motivation was consistent throughout. And then after 3 cycles, we took an MVC. Again, we didn't want to do an MVC after every cycle here because of what I just mentioned. It can confound our overall experimental results. So we had individuals come in on 3 separate days. They performed the 20, 40, and 60 in a counterbalanced order. And again, we used dependent variables of AEMG, mean power frequency, MVC, RPF, as well as rating perceived exertion. Okay, and then we looked at the last plateau of each cycle, and we used this area to calculate our EMG amplitude and our mean power frequencies, a lot of our dependent variables. And all of our fatigue measures were normalized to baseline values, again, just to kind of keep standardized across all of our participants. And so what we found is that looking at the low duty cycle, medium, and high, so this represented 20, 40, and 60% duty cycles, we saw that there was about a 5% larger decline in strength for that high duty cycle condition compared to low and medium. Okay, so there was some drop in strength for low and medium as well. And this is to be expected, as we've defined earlier. Fatigue is going to develop during something when you're doing an amount of work. The question is it too much fatigue? Right. So it also did show us that maybe there isn't similar fatigue while you're working at those different areas of that TLV curve. Okay, so this was a pretty strong indicator of that. Looking at our EMG measures, this is EMG amplitude. And as you would kind of expect, they were different amplitudes just because we were working at different workloads, right? The low duty cycle condition allowed you to work at higher percent contractions. So it made sense that these were higher. We had a little bit of an anomaly here from start to our 3rd cycle, but overall, there were no noticeable time effects here. But for mean power frequency, which is, again, a very common metric used to evaluate fatigue, we did see more of a drop in our mean power frequency, which is indicative of muscle fatigue, right? Or more substantial levels or a different progression of muscle fatigue in this high duty cycle condition compared to medium and then low again. Okay, we looked at RPF as well. We had a lot more variability in these data, despite the familiarization protocol. But, just kind of visually, we can see, the high duty cycle was quite a bit higher, but not statistically significant. What I did find interesting though is that the low and medium duty cycle conditions, they mapped on very well with what we saw for the strength. Okay, so this again kind of did lend, I guess, strength to that familiarization protocol, because they were rating their fatigue roughly the same to their level of decline in strength, right? And we look at the high duty cycle condition is the same in terms of their decline in strength. Okay, so overall, working at different duty cycles along the TLV curve produced different fatigue responses. The high duty cycle condition, or this one here, had the most prominent fatigue response. And, we should note that this was just after 1 hour. These TLVs and the MAE is actually designed for an 8-hour work period. So, the fact that we were seeing the level of fatigue that we did, about a 10% decline here, same with our mean power frequencies, a fairly significant decrease. That's definitely something to look at further. So I guess the question, why is this the case? In general, higher duty cycles, by definition, mean that there's less rest. Okay, and the idea behind the MAE and the TLV is that we can account for having less rest by lowering the intensity at which we're exerting our contractions. Okay, so what this would just suggest, if we're seeing a different fatigue response at a higher workload, it likely just means that the force level is too high at these higher duty cycles. Okay, and one thing to note though is the MAE does actually have a little more of a conservative recommendation at these higher duty cycles. The MAE is forced down to 0 at 100% duty cycle. So it assumes that if you're working with no rest at all, you shouldn't be able to do any force, right? Or you shouldn't be recommended to do that at all. Whereas the TLV it'll say that you can do about 6.6% MVC. In fairness, they recommend that it shouldn't really be used above 90% anyways, but it still does influence the shape of the curve at the higher duty cycle range. So, we do know, although some work has suggested that it's possible to sustain low-level isometric contractions indefinitely, most evidence indicates that activation at any intensity will eventually elicit fatigue. Okay, so that definitely is something that this study kind of highlighted for us. Okay, so some limitations. Again, it's a 1-hour protocol versus the intended 8-hour threshold limit. So it still produced differences in fatigue development. We should note too that as part of our protocol, we did include maximum voluntary contractions. So that, of course, will also contribute to the fatigue, but that was consistent across all of our conditions. So hopefully that effect would mostly have washed out. We also looked at an isolated task. As we all know, in the workplace, things are more complex than that. We work at often different force levels. Duty cycles might be different from cycle to cycle. Okay, so this is a little more simplistic evaluation, but kind of where we needed to start. It's a convenient sample. We used university students. Experienced workers might have different strategies over time. Right? And there's a lot of more on the neuromechanics side here. We have different synergists that contribute to this. We didn't necessarily track all that. Okay, but overall, in terms of future directions for this, so one thing we want to do in the future is do some further validation using advanced fatigue models to further refine these thresholds. So something like this, we can use, let's say, for example, the motor unit fatigue model that Jim developed, or Mike Stahn's fatigue model. And if we were to evaluate all of these conditions using a fatigue model, we might be able to just gain some more information on, clearly the upper right corner is just always going to be extremely unacceptable, and you won't be able to do that for very long. But what's actually happening throughout close to the curve, let's say plus or minus 5 or 10% from the curve, we might be able to gain some insights on that. And then also evaluation of more complex force profiles and dynamic tasks. So just bringing back a little more more realistic scenarios and try to study those in the lab. And really my main question is, can the MAE or TLV equations be used to account for more complex force histories? So we did show this in some of my postdoc work, that using amplitude probability distribution functions, I'll show you in a second what those are, but we actually think that we can do a pretty decent job using this approach and comparing that to the MAE and the TLV. And then another thing we could do is just do more psychophysical studies that look at dynamic versus static exertions, just to prove if we can use, let's say, the MAE or the TLV for more complex tasks. So this is, again, work from Clark Dickerson's lab when I was there. And we did a shoulder fatiguing protocol here. We had one higher up, one at shoulder level, one at umbilicus height, with the idea that the higher hand location would result in more fatigue in the shoulder. Right? And we did show that experimentally, but if we were to plot everything as an APDF, which basically you can think of it as all the EMG amplitudes that we measured, if we rank them from the lowest amplitudes all the way to the highest amplitudes that was observed in the signal, that can essentially be thought of as being a duty cycle as well. Right? It kind of tells you for 40% of the time we were at least this level of contraction level. Okay, so when we use this approach, we were able to see that the high condition, we actually were above that MAE, or that recommended MAE, for greater than 90% of the time. Okay, and that was further confirmed looking at our more traditional fatigue metrics. So we do think that there is some potential here using this approach, and this is something that Ryan Foley, my PhD student, is going to kind of dive into a little bit further. So final conclusions: RPF, definitely it's easy to implement by researchers and employers. It is a robust and efficient fatigue metric whose accuracy can be improved with some familiarization or training. Okay, so I see this as being a very valuable tool for us. It takes a little bit of extra time at the beginning, but this can be a really nice window into what's actually happening without incurring some extra fatigue by actually measuring MVCs all the time. Okay, and then the main question was the current TLV that's out there is not quite equal in avoiding excessive localized muscle fatigue. So when we're considering task redesign, and say you have the option of reducing duty cycle or reducing the effort level, this is just saying that reducing that duty cycle or adding more rest time might be a more potent mechanism to avoid fatigue accumulation rather than reducing effort or intensity. Right? Based on the current TLVs, we might want to err on the side of having lower duty cycles, and even though you're working at a higher overall contraction level. And as of now, too, it kind of suggests, especially if you're going to be working at higher duty cycles, that you should probably consider to use the Potvin MAE equation, as it is a little more conservative in that upper range. So we'll still have to test that, but this is definitely my recommendation at this point. So I just want to thank you all for your time. Especially want to thank my co-authors here, co-contributors to this project. This was Dan Muller's thesis, as well as Ryan Foley, Dr. Jeff Graham, and Fahima Wakili, who are members of the lab, contributed quite a bit to this, as well as the funding sources who have really kind of kickstarted my research program. I'm excited to keep going here in the next few years. And yeah, I just wanted to give a special congrats. I don't know if he's in the call here or not, but just last week, literally a week ago, probably around this time, Jim was awarding the IEA Triennial Outstanding Educator Award. So I just wanted to let the CRE-MSD community know that kind of one of our own just had a very large recognition there. So as you can see, kind of his work is imprinted in a lot of what I've been doing over the last couple of years. So I just wanted to give this special congratulations to Jim. So with that, thank you for your attention, and happy to take any questions.
Thank you so much, Nick, and thank you. You did a great job. You stayed on time, and I'm going to jump right in now to the questions that are coming in. First question we have is, what would you say is the acceptable EMG results in upper limb localized fatigue based on the result? Can we say that the worker must stop the work and the workstation needs to be improved?
Yeah, so good question. I would say that, looking at EMG just in isolation, just for at one time, would be tough to give you that answer. What we could do is compare to standards. So for example, the Janssen APDF limits. So that approach, for example, will say for our low level or prolonged or static EMG exposures, you really shouldn't be working greater than 2%. So if in an isolated task, or say for dental hygiene, we measure an exposure that's at 4 or 5%, we know that that is likely to extrapolate, day over day as that worker continues on, that's likely going to lead to some problematic, some maybe development of pain over time or MSD over time. So I would say, if you measure MSD or measure EMG, just looking at the amplitudes in isolation gives you a little bit of information, but what's more valuable is if you can compare those to certain thresholds that are out there in the literature, which is kind of why I'm very interested in this, just to keep on continuing the work and validating some of the thresholds that exist and maybe move towards newer thresholds that we can use in the future.
Thanks, Nick, for that. The next question that we have, first of all, the comment was made, thank you for this awesome webinar. It's always good to hear those type of comments. Aside from the DC repetition load, what factors do you think are most important to consider at the individual level that modulates fatigue progression?
Yeah, again, a pretty tough question because, when we look at all these curves, they're kind of based on average population data. So, at the individual level, there are other factors that can be considered. So things like sex, for example. In general, females tend to be a little more fatigue resistant, especially at lower levels of contraction. So that can play into things as well. Things like age, for example. So there are individual factors that can be, I guess, looked at if you want to tease into things a little bit further. But a lot of times, what you want to do in these types of studies, specifically EMG studies, is not measure it just on one person. You want to kind of get a nice sampling from the population, especially if you're going to be comparing it to that 2% threshold or line in the sand, or 2.4% if it's the MAE you're comparing to. And the reason for that is, in any one measurement, say I bring a participant into the lab or you measure someone in the field, you might just not get a good MVC or you might like a good voluntary contraction. And if that's the case, the EMG might look a lot elevated compared to what it actually is. Okay, so we kind of protect against that by measuring a larger sample of people and then looking at the overall average result. So I don't even know if I did a great job answering the question. Feel free to let me know if not.
I think you're getting there. He certainly extrapolated a bit more, and maybe I should have read this part to you. Would you consider the micropause of 2 to 10 second complete muscle resting? And could that impact reducing the 8-hour workday muscle fatigue?
So yeah, I guess that all is important. The fact that not all work tasks are the same. Some are going to have larger rest periods compared to others, whether they're kind of micro breaks or, say you work for 30 consecutive seconds and then you get a 30-second break. All of those can influence the progression of fatigue for sure. And those types of things can be studied using fatigue models. So, things where you can actually input those force profiles and try to predict how fatigue will develop. And I don't know, I haven't run those scenarios, but I'm sure there will be differences with that. But overall, and that's something that I think definitely needs further study moving forward. But overall, right now, can we just use duty cycle, which basically it kind of removes that factor of whether it's micro breaks or whether it's longer duration breaks, and basically just looks overall of effort versus overall time. That seems to be a pretty robust approach right now. But definitely, I think something that we can do a little further study on.
And just a quick segue from that, would you say that this work has significant application into the keyboarding challenges and fatigue and MSDs that people experience with long days of keyboarding?
Yeah. I guess it can, because at the end of the day, it's you're kind of exerting. The force profile will look a lot more complex compared to some of the ones that I was showing. I guess the only issue with keyboarding is that they're very low force levels. But yeah, I don't know. That's a good question. I'll have to think about it a little bit further.
Yeah,
I definitely think it can be used. Like if you can estimate or get a good estimate of how much force you're exerting while typing, and I'm sure the data exists out there for that. Some people might be heavier typers compared to others as well, but theoretically you can evaluate that using this sort of an approach, right?
I was just wondering about the transferability of this model with, the last 16 months of people working from home, and if that's, something to look at, also given the equipment that people are using and the keyboarding effect,
Hmm.
based on, the force of the typing or not. Anyway, it's just something to think about, and again, an application of your going forward.
Yeah, yeah, I can definitely see that occurring. So in that case, you'd likely be at a very high duty cycle, just because oftentimes you type without too much rest.
Right.
And if that typing just happens to be a little bit above that force level, and the thing is too, some of these things can be amplified by things like posture, for example, or, are you basically in a position where you're occluding blood flow, or you're putting pressure on your carpal tunnel. Some of these things can also influence. It's not necessarily just the force, but the force can be also affected by the posture that you're in as well. So yeah, it's
Thank you.
something to definitely consider.
Very, very useful. Thank you for that. And what do you think of the kinematics-based methods to drive the measurement of fatigue progression?
Kinematics-based
Yeah,
methods.
yeah. Sorry, I'm
Yeah.
tongue-tied today.
Oh no, me too. Yeah, so that's something that we've looked into. It's certainly something that's of a lot of interest because oftentimes that will be related to things like productivity and general performance of a task. So it's something we looked into as well during my postdoc. We did a study with Rachel Whitaker, just looking at kinematics and seeing if we could detect if there were any observable changes in the kinematics pattern. And if that occurred roughly at the same time point as when we noticed these more significant fatigue exposures or fatigue indicators. So yeah, that it definitely is linked with it. We do tend to see that in the literature that, as fatigue progresses, we definitely do start to see changes in kinematics and potentially kinetics as well. So the problem is it's a lot more difficult to potentially measure that. Like EMG on its own can be a challenge, especially in the field to measure. So kinematics can be a challenge as well. And I think, as you all know, if you attended IEA the other week, there's a huge push now into artificial intelligence or machine learning based assessments of kinematics. So I think that will open up a big door into looking for, can we detect any changes in kinematics now? And from that, determine if there are any, any fatigue that might be developing. Specifically, is fatigue developing to the point where now we are at we're working at a poor posture, or we're changing our kinematics and mechanics to a point where we're more likely to develop an injury from that.
Thank you so much, Nick. You have given us just great baseline foundational information for applying to our work, no matter what sector it is. And I want to thank all of our participants for joining us today. We really appreciated your attention and your questions. And in fact, I think based on today's presentation and the response we had to your webinar, Nick, we will be following up with you and your graduate student just to see what's coming up next out of your lab.
Well, thank you very much. And I can't kind of overstate the importance of that CRE-MSD seed grant, because I kind of walked in with very limited funding, and that CRE-MSD seed grant really gave me the push I needed to really get rolling on this research, and it's really kind of snowballed since then. So I just wanted to say thank you one more time for that
Well,
to the
thank you so
organization.
much. And I will let the participants know that we will be issuing a seed call, grant call in towards the end of summer, hopefully end of July, with applications due in September. And we are looking to award more seed grants this year, and as well having an open call so we can respond to urgent and rapid thematic needs based on the trends in the industry and ministry criteria. So please watch for that, and we look forward to engaging with all of you in the near future. Thank you for joining us today, and thank you again, Nick. Just a wonderful presentation.
Thank you very much.